So today we're going to be talking about sig figs. And sig figs are one of those things where I know they're annoying, it's just we have to do them. So they do seem really silly, but they do have a purpose. So where significant figures come from is kind of like if you've ever done research. When you report data, you can do like a percent error or calculating error to see basically like the range of numbers where you expect the true answer to be. So when you collect data and do the math, you have numbers to support kind of a range, but it's not always going to be that exact number. And it's not like that number is always the true answer. So there's kind of like a range of acceptable numbers. So I kind of think of it like if you have glasses, if you take off your glasses and look in the distance, usually you can see like fuzzy shapes and colors, but you can't see like the specific outline of anything. So it's kind of like that. Sig figs are that rough estimate. So here in this graph, it's just an example I found on Google. There are these error bars, okay? So it's basically saying like we calculated the top of this line here, but the true answer is likely between this top line and bottom line. So significant figures are kind of related to that when it comes to measurement. So it tells us basically how confident we are in the data. So for example, if we have two scales and one records the ones place, so it gives you no decimals, and one records the hundredth place, which is 2 decimals, the second one is a more sensitive instrument and gives you a more accurate answer, so you can be more confident in that measurement. So for example, when we did online learning, I did a popcorn kernel lab where we calculated the percent of water in popcorn kernels. When I first started the lab, we have a kitchen scale, but it only reports to the ones place, so it doesn't report any decimals. So when I ran through the lab with that scale, I was not able to detect any change in mass, which is the amount of water that is in the popcorn kernel. So I had to run to school and get a lab scale that basically gives me 2 decimal places. And when I ran through the lab again, I was able to get that data. And the reason is that that first scale I was using wasn't sensitive enough to detect that change. So for example, if we measure something at 32 grams on the first scale, it could be anywhere between 31.5 to 32.444, whatever. So there's a large range of numbers that could be the true value. On the second scale, that range of true values is much, much smaller because it's confident in those last couple of decimals. So a scale that reports the 3 decimals would be even more accurate than that second one. When we record a measurement, we report every number that we are confident in or know, plus one place that is estimated, whether it's at ones place or a decimal place. So for any digital instrument, like that scale example, or if you have a digital thermometer, a pH meter, something like that, the instrument does that estimation for you. So that's why in lab, if you're making a measurement, weighing the mass of something, you might notice that last digit kind of jumps around a little bit. That's because it is the estimated digit. So it is an estimate, it's not exact. So for the 32 gram scale of the first one, the scale knows that the object is at least 30 grams and it is estimating the ones place. So it's estimating a 2. For the second one, it knows the 30 grams. It knows the 2 grams. It knows the 0.0 grams. What it doesn't know is that hundredths place, that last digit, and it's estimating that last decimal place. So again, that's usually why you will see the scale, it might jump around a little bit when you are making measurements. For any measurement or instrument that has lines, kind of like a manual instrument, for like a graduated cylinder or a thermometer that's not digital that has those lines on it, you have to make the estimate. So you have to say what you know and then estimate one place. Generally, more lines is more precise, but that's not necessarily true. So there is something called a volumetric flask, which is very, like, extremely precise, and it only has one line because it's precise for that one measurement. But in general, more lines would be more precise. So let's consider a beaker and a graduated cylinder. Here we have a beaker with some mystery liquid in it. Looking at the beaker, I'm confident that the liquid is between 400 and 500. I know it's past 400. I'm not quite certain that it's reached 500. So I'm confident in 400, that digit place. There is no line telling me where 450 is, or 410, 420, anything like that. So where I'm estimating is actually going to be the tens place, because there is no line to tell me that I've reached 450 or anything like that. I only have a line that tells me the hundreds place. So I'm going to estimate that the liquid is at 490. To me, it doesn't look like it's reached 500. So I'm going to report that there are 490 mils of water in this beaker. I can't say 491, I can't say 499, because there's nothing telling me that is in the 90s tenths place. So my estimate is that second digit. For a graduated cylinder, there are typically more lines, and it's hard to kind of read these numbers and everything. I did my best. But I know that the liquid has reached 450, and each of these little lines is worth 5 mils. So I also know it's reached 475, which is this line here. The line is between 475 and 480 milliliters. It looks like it's closer to 480 to me than 475. So I'm going to estimate that ones place to be 479 milliliters of liquid. A lot of the instruments that we have, like in the classroom, each line would be 1, in which case you would be estimating not the ones place, but that first decimal place, the tenths place. So sig figs are really, we use them when you're given a number, not necessarily when you're given measurements. But the reason that they have them and that they exist is because of measurements. So in problems, you're given hypothetical values or hypothetical measurements. So there are rules for determining how many sig figs are in a number, which is important when we do the math for reporting sig figs. So the rules for determining if a number is significant or not, basically how confident we are. Non-zero numbers are always significant. So any number 1 through 9, always significant. A 0 between two non-zeros is always significant. A 0 that is before a non-zero number is never significant. And a 0 that is after a non-zero is only significant if there is a decimal somewhere in that number. We'll go through examples to see these. So here I have some examples. We have the number 360. It has 2 sig figs. They are 3 and 6 because those are both non-zeros. The 0 is not significant because there is no decimal place. Here, this is not significant, this is not significant, and this is not significant because they are all zeros before a non-zero. 2 is a non-zero and 5 is a non-zero, so I have 2 sig figs. For the next number, I'm going to start the same way. Not significant if it's before a non-zero, significant because it is a non-zero, and then we have this 0. Remember, a 0 is significant after a non-zero if there is a decimal somewhere in the number. Here we have a decimal, so that tells me that this is significant as well. So I have 3 sig figs here. Here I have a 4 and an 8 that are both significant, and then in between them I have a 0 that is sandwiched. Any 0 that is between non-zeros is always significant, so I have 3 sig figs here. Here I have a non-zero, and then a 0 following non-zero. 0 following a non-zero is only significant if there is a decimal place somewhere in the number. Since there is that little decimal place right there, this is significant and we have 3 sig figs. Different than this 360 because this does not have a decimal place. And then finally we have this 650. So again, we have 2 non-zeros that are both significant. And then we have 2 zeros here, both significant because there is a 0. So we have a total of 4 sig figs. We have rules for adding and subtracting and multiplying, dividing sig figs. So for addition and subtraction, the final answer that we report is based on decimal places. So the final answer is going to have the same number of decimal places as the answer, or the number rather, with fewer decimal places. For multiplying and dividing, it's not based on decimal places, it's based on significant figures. So that's where being able to determine significant figures is important. So for multiplying and dividing, you're going to have the same number of sig figs as the number with the least number of sig figs that you started with. So here are some examples. If we have 2.35 minus 0.0058, I plug that into my calculator or do written math. I'm going to report to 2 decimal places, and I know that because 2.35 has 2 decimal places, and this one has 4. 2 is less than 4. So to find the answer, once I plug into the calculator, it spits out 2.344200. Lots of numbers. Now all of them are going to be reported. I only report 2 decimal places, so that's 2.34. The number following the 4 is a 4, so I'm going to keep it 4, 2.34. If it was a 9, 2.349, I would round to 2.35. So rounding rules are still the same. Here I have 18.02 divided by 9.03. Here we have 2 numbers and it's multiplying or dividing, so I have to count the number of significant figures. 18.02 has 4 significant figures, 9.03 has 3 significant figures, so I'm going to report my final answer with 3 significant figures. Once I plug into the calculator, I get 1.995, and then I think a few other things. But I am going to round to 3 sig figs, which would be 1.99, but then this 5 tells me I'm going to round up. So I'm going to round up to 2, but I can't just say 2. I have to have 3 sig figs, so it's 2.00. Oh, I guess I did that twice. That's fine. Honestly, on the AP exam, sig figs do not matter except for a problem where you are reading a picture of an instrument. So like those examples we did with the beaker and the graduated cylinder. And typically on the AP exam, it's going to be a burette. For those calculations that you do on what's called the FRQ, the long answer, the written answers, typically it's good to carry as many decimals as possible while you're doing the math. And then in your final answer, usually reporting 2 or 3 decimal places is good. So they will not count necessarily against you if you use the wrong sig figs in an FRQ unless you are reading a picture of an instrument. But it's still good to know and still important to know, just the thing we got to cover. And it is in your summer homework, so I wanted to help you out with that. Have a great day.